Scientists said they achieved fusion ignition, but the power plant is still nowhere in sight. So what did they actually do? Fusion is the same process that powers the sun. You take two light atoms, squeeze them together hard enough, and they merge into a heavier atom, releasing a burst of energy in the process. The atoms used in most fusion experiments are deuterium and tritium, both forms of hydrogen. They fuse more easily than other combinations, which is why researchers keep coming back to them. The hard part is getting those atoms close enough to fuse. Atomic nuclei are positively charged, so they repel each other. You need enormous heat and pressure to overcome that repulsion. We are talking temperatures hotter than the core of the sun. Ignition has a specific meaning. It is the point where the fusion reaction itself produces enough energy to keep itself going. Without needing constant energy pumped in from outside, the fuel starts heating itself. In December 2022, a lab in California called the National Ignition Facility crossed that threshold. They fired 192 lasers at a tiny pellet of fuel, and the fusion energy that came out was greater than the laser energy that went in. That was a genuine milestone. For the first time, a fusion experiment produced more energy from the fusion reaction than the energy delivered directly to the fuel target. Scientists call that energy gain greater than 1. But here is where it gets complicated. Those 192 lasers required a lot more electricity to run than the energy they delivered to the pellet. So the overall system, wall plug in, electricity out, still lost a lot of energy. Think of it like a car engine that burns 1 liter of fuel but needed 10 liters to build up enough pressure to start. The combustion worked, but the whole system is still deeply inefficient. There is a second approach that does not use lasers at all. Tokamaks use powerful magnetic fields to hold superheated plasma in a donut-shaped chamber. The ITER project in France is building the largest one ever made. Tokamaks have their own challenges. Keeping plasma stable inside magnetic fields is genuinely difficult. The plasma wants to escape, and any disruption can shut the reaction down instantly. Beyond the physics, there are serious engineering problems that nobody has fully solved yet. Tritium, one of the fuels, is rare and mildly radioactive. The intense neutron bombardment from fusion gradually damages reactor walls. A working fusion power plant would also need to convert all that heat into electricity reliably, run continuously for years, and do it cheaply enough to compete with other energy sources. None of that is guaranteed. Ignition was a real scientific achievement. It proved the physics works at that scale. What comes next is an enormous engineering challenge that researchers are actively working through with no fixed finish line. If you want to understand what separates a working experiment from a working power plant, the engineering gaps are actually the most interesting part, and that is worth exploring further.